So the next section is section 3.1.2, understanding probability. In this particular topic or section, we will explain the role of probability in statistics. So there are a couple of key terms that I want you all to know. The first thing is the definition or the meaning of probability. It's the proportion of times an outcome would occur if we observed the random process. The key word is the random process, an infinite number of times measured on a scale of 0 to 1. In the other word, they're simply saying, hey guys, the probability can be anywhere from 0 to 1. 0 to 1 inclusive. That means if the probability is 0, it's impossible it's going to happen. If the probability is 1, I am 100% sure it's going to happen. That means you're certain it's going to happen. It's as simple as that. Now let's look at the next keyword. Statistically significant. If the measurements or the observations from the experiment that you conducted are unlikely to have occurred by chance. That means, you know what, I don't, like when you go to a Starbucks store and you ask 50 people if they like coffee, by default the answer is going to be yes. So you know it's very unlikely that they will say they do not like coffee. So when you're doing a statistical experiment, you always have to be random when you're picking your sample, and the results you get from the experiment are unlikely to have been occurred by chance. So the statistical significance means the significance level of an event is that the probability that event could have occurred by chance. If the level is quite low, that means the probability of that event occurring by chance is very low. That means it's statistically significant. There's one more key term that we have to do before we jump right into our problem. So let's take a look at that. Quantifying statistical significance. What does that mean? If the probability of an observed result occurring by chance is 0.05 or less, then the difference is statistically significant. So what I'm saying is, if the value of that event occurring is less than 0.05 by chance, that means it's statistically significant. If the probability of an observed result occurring by chance is 0.01 or less. Now you might be asking me, Miss, where are they getting these numbers 0.05 or 0.01? We will learn more about these numbers once we get into hypothesis testing. But as of now, you have to understand if the probability is less than 0.05, then the difference is statistically significant. So if the probability of an observed event is less than or equal to 0.01, then it is statistically significant. That means you're telling me that the probability of that event happening by chance is very, very small. So it's not happening by chance. It's happening because of the results or because of the association. Now let's go ahead and look at the next problem here. What I want you all to do is, I don't want you all to look at the options. I want you all to tell me what your thought process is. What did you conclude once you read this problem? So here is the problem. You ready? The mean body temperature of human is accepted to be 98.6. We all know that, especially during this COVID times, because we check our temperature every day. In a study, the body temperatures of 127 individuals were measured. So imagine I tell you, I say, you know what, the body temperature is 98.6. And you're like, okay, miss, I'm going to do an experiment. And you take the temperatures of 127 individuals, right? And you measure their body temperature. And when you find the average, which is what's happening in the problem, the mean body temperature was calculated to be 99.7. So you take the temperature of all these 127 random individuals and you calculate the temperature to be 127. And you say, miss, you said it's 98.6, but I got 99. So let's forget about probability. What are you thinking in your mind? You're thinking probably it's not 98.6, right? Isn't that what you're thinking? If you did the study genuinely without taking the temperature of sick people, or just the random genuine study taking the body temperature of a normal healthy human being, and you got 99.7, even forget about stats, even without me telling you, you think it may probably change these days, right? Okay, so let's go ahead and look what happened. So the study of the body temperature of 127 individuals were measured. The mean body temperature of individuals were calculated. Assuming the regular body temperature of human is actually 98.6, the probability of these results, I reread it again just to emphasize this, the probability of these results occurring by chance is less than 0.01. That is, it's less than 1%. I'm telling you, hey guys, something like this happening by chance, it's less than 1%. That means it's very, very low that this happened by accident. What does that mean? That means this is true, or this is really happening, right? So the way to do it is, in probability or in statistics, you don't make a statement because there's always a chance you will make an error. So let's go ahead and see what the options are. We can expect the mean body temperature, we can expect the mean body temperatures of 127 individuals is 99. We are not here to expect, we are trying to do a study. The mean body temperature of humans is not 98.7. You do not make a statement in statistics because there's always a chance you're going to make an error. At 0.01 level of significance, the mean body temperatures of human is not 98.6. This could be valid because not only you are telling me the level of significance, but you're also telling me that at this level of significance, the body temperature is not 98.6. Again, keep in mind, you're not telling me it is 99. You're just telling me, hey, maybe that's not true. That's what you're telling me. Since the human body temperature varies, the result of the studies are not unusual. Again, this has nothing to do with my problem. So the way to look for your option is you will be looking at, let me go back, and you will be looking at 0.01 in your options. And the only option that has 0.01 is this option. So this one is telling me, according to the level of significance, what I found out that the mean body temperature is not 98.6. Again, how do I know that? You always start with what you assumed. You always start with what you assumed. Either you prove this or you disprove this. So what I'm saying, hey, you assumed it's 98.6, and according to my study, it is not 98.6. All right, now let's look at the next problem. All right, so the next problem here is, one symptom of asthma is coughing. What? They're all talking about temperature, asthma, coughing. I hope they didn't do this one right before COVID. But anyway, one symptom of asthma is coughing. In a clinical trial, a new drug intended to treat asthma. Okay, very good, very good. So what happened when the drug was intended to treat asthma? What do I have here? Where is it? 4 out of 90 subjects in the treatment group experienced cough, and 12 out of 150 subjects experienced cough in control group. So now you might ask me, what is control group and what is a treatment group? What happens in statistics is you have, when you're doing a study, I don't know if you'll ever heard, but in radios they ask looking for adults 21 to 30 age, or whatever age. So when they usually do a study, they take a group of people, right? And they divide those group of people into 2 equal parts. One is the treatment group, one is the control group. So what they do is, both these groups have the same symptoms, everything's absolutely same. They give the treatment to the treatment group and they give nothing to the control group. And then After giving the treatment, they take the results from the treatment group and compare it to the control group. And if anything changes, that means the drug is working. If it's not changing, that means the drug is not working. All right, so now let's go back here, and I have 4 out of 90, and I have 12 out of 150. Now, 4 out of 90 is approximately 0.04, and 12 out of 150 is twice, so 0.08. So now let's look at the math here. So you are giving a drug, and in the treatment group, only 4% experience cough. In the control group, 8% experience the cough. So what does that mean? Does that mean that the treatment is working? Yes, because there are less people experiencing cough, and here in the control group, there are more people experiencing cough. It's like only 4 out of 100 of them are coughing, but here 8 out of 100 are coughing. Do you see the ratio? Okay, now that the ratio is taken care of, let's look what happened. The difference is calculated to be significant. So I know that there's a significant difference, but what level? At level 0.05. Remember what I told you? When they give you the level of significance, your answers should also have that level of significance. So blindly when I look, this one does not have the level of significance. This one does not have the level of significance. This one does not have the level of significance. The only thing that has a level of significance is this, but let me go back and check one more time. So what happened? Only 4 in the treatment group are coughing, but 8 in the control group are coughing. So in my mind, the treatment is working, right? So at 0.05 level of significance, the new drug is effective at reducing asthma. There you go. Let's take a look at the last problem here. A standard roulette wheel with slots labeled 0, 0, 0, la 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 la, all the way up to 36 is spun 60 times. Of these spins, the number 7 is spun 7 times. Assuming the wheel is fair. Okay, so what's happening? Always take a step back. Think about the problem. So you are playing roulette, 0, 0, 0, 36, blah, blah, blah. It's spun 60 times. The number 7 is spun 7 times. Assuming the wheel is fair, is absolutely fair, the probability of this occurring is 0.00001. Wait a minute. 0.00001, that means the probability of this occurring is so low, right? Okay. Do these results have statistical significance at 0.01 level of significance? Now, what does that mean? For me to go back and explain this better, let's go back and see the key term. What does this say? It says if the probability, if the probability of the observed result occurring by chance is 0.01 or less, the difference is statistically significant. That means something happening accidentally is wrong. That means this is happening for a reason. So what do? You always compare your probability to 0.001. If it's equal to or less than, that means it's statistically significant. Now let's go back and see. So here, what do I have? I have So my probability is 0.00001, and I'm comparing it to 0.01. So this is definitely less than this. So if it is less, that means it is statistically significant. So yes, the probability of the results occurring is less than 0.01. So they're asking you, do these results have statistical significance? Yes, they do. Why? Because 0.0001 is less than 0.01. So always keep in mind, you take your probability, compare it to your level of significance. If it is less than or equal to your level of significance, that means the results are statistically significant. All right, for the next topic, which is frequency distribution and probability distribution. Frequency distribution contains the number of times each possible outcome within a study. Probability distribution is exactly the same as frequency, but it contains the probabilities of a discrete random variable. And keep in mind, probabilities always add up to a 1. So that's the first key term. Now let's look at the second key terms here. I don't know why they're called key terms, but anyway. Properties of probability distribution function. So you see that probability is always between 0 and 1, right? And when you add all the probabilities, they have to add up to a 1. So these you have to memorize. Probability is between 0 and 1. And when you add all the probabilities, it will automatically add up to a perfect 1. Now, once we know this, let's go ahead and jump into the problems. All right, let me go ahead and pick a nice pen here. I'm going to pick a red color. That's good. All right. So a news program reports 37% of the population are in favor of a certain issue. The key term is 37%. 42% are against the issue, and the rest are undecided. So 37% is for, 42% is against, so 21% are undecided. Now you might ask, Miss, how you got 27%? So when you add all of these up, you need to end up with 100%, right? So now in favor of 37% as decimal is 0.37. Against 0.42, undecided 0.21. And that's how you fill up your probability distribution table. As simple as that. Now let's look at the next problem. So here they say an altered dice, let me just move my mic. An altered dice has 1 dot on one face, 2 dots on 3 faces, and 3 dots on 2 faces. So let me see if I can draw a dice here. Wish me good luck. Oops. All right. So this is my dice right here. So one face has 1 dot, the other one has, it's a 2 dots on 3 faces. 1, 2, 3, 1, 2, 3. 1, 2, 3. All right, you know what? A dice has 6 faces, right? So one face has 1 dot. 3 faces have 2 dots. 2 dots on 3 faces. So 2 dots. This is so confusing. And 3 dots on 2 faces. 3 dots on 2 faces. So totally 6 faces? Yes, very good. Now what are they asking me? If the die is rolled once, so when you roll the die, let x be the number of dots on the upturned face. Construct the table showing the probability distribution of x. Now, so the dice only has either 1 dot, 2 dots, or 3 dots. So you can roll it as many times as you want. You will only get 1, 2, or 3, right? So that means I will get either 1 dot, or I will get 2 dots, or I will get 3 dots. Now they're not asking me what I will get. They're telling me construct a probability distribution. All right. So the probability of getting 1 dot. Remember, how do I find probability? So probability of getting 1 dot. In a dice, I have 6 faces, right? But how many faces have 1 dot? Only 1 face. So the probability is 1 over 6. Now let's find the probability of getting 2 dots. I have 6 faces, How many faces have 2 dots? 3. Remember they said 3 faces have 2 dots? 3 over 6 is 1 over 2. Now probability of getting 3 dots. Again, it's 6. How many faces have 3 dots? Only 2 faces. 2 over 6, which is 1 over 3. You can actually cross-check by adding all of these. You should end up with a total 1, which you will. All right, the last problem for today would be for a probability distribution of x given below, find m. They did not give us any numbers, but they just said x is 1, the probability is m, it's 2, it's 2m, 3 is 3m, 4 is 4m. What do I know? I know that the sum of all probabilities add up to a 1. That means, I want to change the color to blue. That means m plus 2m plus 3m plus 4m should give me a 1. So when I add m plus 2m, 6, so I have 10m. So change the color again so you can see the difference. So 10m is equal to 1. M is equal to 1 over 10, which is 0.01. Hope this helps. And if you have any questions, don't hesitate to email me or call me.